Good morning friends, welcome to the lecture 2 of Operation Research. In today's lecture, we will learn linear programming. We will learn its introduction, representation and problem formulation. So before starting the linear programming, let us first summarize what we have studied in the last lecture. We have studied the definition of the operation research, which is defined as analytical approach of problem solving using a mathematical tool or technique. It was developed in 1936 before the World War II by the British Army in order to have a optimized solution. The steps involved: first identify a problem, then develop the model using a tool or technique, apply that developed model, validate the model and apply the model to the real life problems. The application of operation research are analyzing data, forecasting, identifying best tool and techniques and better scheduling, etc. The tools and techniques of the operation research are linear programming, transportation and assignment problem, game theory, sequencing, stochastic model, queuing model, CPM and PERT. So in today's lecture we will focus on the linear programming. Introduction. Linear programming, sometimes also called as LP, is a method utilized to solve a linear objective function and linear constraints. It determines the actual values of the linear constraints that optimize the objective function. Let me give an example to explain what we have to do in linear programming. Suppose you want to obtain the maximum number in your coming semester and you have 5 subjects, operation research and some other subjects. So after studying 4 months you find out that you are very much strong in operation research while you are not that much strong in 1 or 2 subjects. So in order to obtain the maximum marks, what you will do? You will focus on those 2 and 3 subjects on which you have command and you will try to obtain maximum marks on those 1 or 2 subjects on which you are weak. Okay, so the objective function, it measures the effectiveness of the problem. For example, it maximizes the profit or minimize the cost. Constraints, also called as decision variables, they are the inputs to the system. For example, cost, time, manpower, etc. Methods. There are 2 methods of solving a problem using linear programming. They are graphical method and simplex method. So first we will study graphical method, then we will study the simplex method. The canonical representation of the linear programming. As explained earlier, it needs objective function and it needs a constraint. So the objective function which we have to maximize can be represented as z equal to c transpose x subjected to the constraints ax less than equal to b and non-negative constraints x should be greater than equal to 0. So where z is a function which we have to maximize, c is a coefficient, t represents the transport and x is the constraint. As written here, where x is the constant variable, c and b are the known coefficients, a is the matrix of known coefficients and t represents the transpose. This canonical representation can also be written as this: z equal to c1 x1 plus c2 x2 plus dot 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 plus cn xn, which can be written as summation of ci xi starting from 1 to n, subjected to the constraints a1 x1 plus a2 x2 dot 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 plus an xn less than equal to b and non-negative constraints. X should always be greater than or equal to 0. Now let us learn that how to formulate the problem. Okay, so our example is given here. First we will read this question, try to understand what we have to do. Okay, then we will formulate the problem. A company assembles 2 models of raincoats, model A and model B. the amounts of material and labors required for each assembly, and the total amounts available are shown in the table. The profits that can be realized from the sale of each raincoat are $22 and $28 for models A and B respectively, and we assume there is a market for as many raincoat as can be manufactured. The manufacturer would like to determine how many of each model to assemble in order to maximize the profit. Okay, so first we have to find out our objective function. Okay, so let us first try to determine our objective function. Objective function, which is z. Okay, so we are getting $22 for model A and $28 for model B. So suppose we are developing QA, which is the number of model A raincoat, while QB is number of model B raincoat. So as we are obtaining $22 from model A, so $22 from model A plus $28 from model B. So this is our objective function. Okay. Now we have to determine the constraint equation or decision variable. The data is given in the table. The data shows that resources required per unit. That means in order to produce one raincoat, we need 8 material units for model A and 8 material units for model B. The resources available, the maximum resources material units available are 3400. Okay, and in order to produce one unit of model A, we need 2 labors, and in order to produce one unit of model B, we need 3 labors, and the maximum amount of labor available is 960. So first for material unit, which says 8 for model A plus 10 for model B. The maximum available is 3400. So it should be less than or equal to 3400. Now for labor, we need 2 labor to develop 1 unit of model A plus 3 labor to develop 1 unit of model B. The maximum is 960. So these are your constraint equation, which is equation 1. This is equation 2. Now we have to also add non-negativity constant. That means QA should be greater than equal to 0 and QB should be greater than equal to 0. So this is your problem formulation. Okay. Now let us go further. This is the example 2. This example is bit difficult compared to the example 1. but we will try to develop the model for this problem. A space agency wishes to set up a schedule for launching satellites over a period of 3 years. Experimental payloads are of two types, say T1 and T2, and each launch carries only one experiment. I just want to tell you here, before solving a problem, try to read the question carefully. Okay, then you will be able to develop your governing equation. Then you will be able to solve the question and get the answer. So the first data is 3 years. Okay, you highlight this part, 3 years. External negotiated agency policies dictate that at most 88 of payload type T1 and 126 of type T2 can be supported. For each launch, type T1 payloads will operate successfully with probability 0.85, that means 85%, and type T2 payloads with probability 75%, that means 0.75. In order for the program to be viable, there must be a total of at least 60 successful deployments. The agency is paid $15 million for each successful T1 payload and $1.2 million for each successful T2 payload. The cost to the agency to prepare and launch the two types of payloads are $1.05 million for each T1 and $0.7 million for each T2 payloads. 1 week of time must be devoted to the preparation of each T2 launch payload and 2 weeks are required for each T1 launch payloads. So first let us develop the objective function. Then we will develop the constraint equation. Let me just change the color. Blue looks good actually. Objective function Z. So the agency, while providing a public service, wishes to maximize its expected net income. That means we have to maximize the profit for the company. So we have to consider the amount that is being paid to the company or the profit which companies is getting after the deployment of the payload. So this is written here, the agency is paid $1.5 million for each T1 payload and $1.2 million for each T2 payload. Okay. So before writing the, let me first, QA is number of T1 payload and QB is number of T2 payload. Okay, so we are obtaining $1.5 million for each successful T1 payload and we are obtaining $1.2 million for each successful T2 payload. Okay, now you focus here on this line. For each launch, the type T1 payloads will operate successfully with probability 85%. That means we have to multiply here by 0.85. Similarly, we have to multiply here by 0.75 because the successful probability of this is 0.75. So this is the profit which the company is obtaining. Now in order to produce these payloads, the company is paying $1.05 million for T1 and 0.7 for T2. So we have to minus it in order to have the objective function. 1.05 for QA minus 0.7 for QB. So let me open the calculator and multiply 1.5 by 0.85. This is coming around 1.275. So here we can write 1.275 QA. Now 1.2 multiplied by 0.75, 0.9. So here we can write 0.9 QB minus 1.05 QA minus 0.7 QB. So the objective function will come around 0.225 QA plus 0.2 QB. This is our final objective function. Okay. Now let us develop the constraint equations. We will focus step by step. Okay. So the actional negotiated agency policies dictate that at most 88 of payload type T1 and 126 of type T2 can be supported. Okay. So Q1 should be less than equal to 88 and QA and QB should be less than equal to 126. This is our equation 1. Okay, and we have utilized this data. Now in order for the program to be viable, there must be a total of at least 60 successful deployments. So we need 60 successful deployments. QA plus QB. The successful probability is 0.85 and let me erase it. Plus 0.75. Okay. This is equation 2. One more data is given, which is here. 1 week of time must be provided to the preparation of each T2 launch and 2 weeks are required for T1 launch, and the maximum amount is given here. A space agency wishes to set up a schedule for launching satellites over a period of 3 years. Okay, so considering a year has 52 weeks, in 3 years we will have maximum of 156 weeks. So 156 less than equal to, we need 2 weeks for QA T1 payload and we need 1 week for T2 payloads. So this is our equation 3rd. Now we can easily write, the non-negativity constraint is already given, which is here. Okay, so this is the problem formulation. This you can solve either using simplex method or graphical method that we will study in the upcoming lectures. Thanks for watching this video. We'll see you in the upcoming videos.